So as I look at factoring this one, the very first thing I do look for is I look to see what can I divide out of every single term. And in this case, there is something I can pull out of all of them. Now, a great strategy when looking to see if you can divide something out of every term is once you see that there kind of is something, like you might have recognized they're all even right at the start. And so you might have been saying, okay, no, there's something then. I will usually look at the smallest number, and I'll just start by looking at all the different things that go into that. Does 12 go into all three of them? No. Okay, the next biggest number that goes into 12 is 6. Does 6 go into all three of them? Yes. So that let me figure out what that biggest number was that is going to go into all of them. It's going to be a 6. So the very first thing I do then is I'm going to write that 6 down out front of the parentheses, and yes, it must be out front of those parentheses, and we still have to include it. And then I go ahead and divide every term by 6. So I'm going to get 2x cubed minus 5x plus 20. And now let's double check ourselves, make sure that we did that right. If I look at all three terms inside the parentheses, is there anything I can divide out of all three of those now? Nope, doesn't look like it. And so, by the way, are there x's in every term that I can pull out? No. If there were, I would do that. But since there's nothing else that goes out of all three terms, I know I'm done with that part. Last thing, sometimes we're going to do these, and we'll be able to take it a step further, where we end up breaking it down into this sort of a problem. Am I going to be able to do that in this case? Well, the answer actually comes from this exponent right here. We can break it down into that when it's x squared. Because this is x cubed, no, we can't. At least not in this particular situation. We will be looking later on about how we can wrangle some of those, but right now, nope, nothing else we can do with it. So this is your final answer, and this is what we were working toward. Then to continue practicing these ideas, please write down and factor this problem. All right, so when factoring this one, again, the very first thing we do is we look to see, is there anything I can divide out of every single term? And is there? Yes. I can divide them all by 2. And so I'm going to start by doing that. I'm going to pull the 2 out front. Remember to pull that 2 out front and leave it out front. It has to still be there for these two to be equivalent. And remember, the whole point of this is that these are equivalent forms. That is, if I plug some number in for x in this, I'm going to get the same number as I would if I plugged x in for this. That's our whole idea here. So it's different ways of writing the same thing. But now in this case, we actually can take it a little bit further, because you'll notice that inside of our parentheses, we do have a quadratic. Note, and I can say that because it's starting with x squared, and that's what tells us that it's a quadratic. And so I am going to be able to break it down one step further. Now in order to do that then, I'm just looking at the quadratic part. I already pulled the 2 out, so all it's doing is just carrying down. It doesn't affect anything else we do inside these parentheses. I'm going to be looking here to see what 2 numbers add to my middle number and multiply to my last number. So, is there a combination that adds to -5 and multiplies to -14? Yes, indeed, it is -7 and a +2. There, we factored the quadratic that was inside of the parentheses. The 2 just hung out front. This is our final answer. This is what we're going for on this one. It is now totally factored. When you see problems like this in the future, you're going to hit times when you do this part, and it's going to be marked wrong. And you're going to be saying, but didn't I do it right? Yes, but just not totally right. We have to actually go all the way down as far as one of these things can factor. And so if you end up with a quadratic on the inside, remember to check and see if we can add to the middle and multiply to that last term there. So again, looking at our polynomial here, we want to see if we can factor anything out of every single term. So as I look at every single term, well, there's no number I can divide them all by this time. But there is still something I can pull out of every single term, because you notice they all involve x's. So I'm going to be able to pull some x's out of every term. The question is, how many x's can I pull out of every term? 3 of them. Yep. Whatever the fewest number of x's are that you see in any of the terms, that's how many you can pull out of all of them. And so we're going to be, in this case, factoring out x cubed. And then that's going to sit outside the parentheses. Now I pull the x cubed out of every single term. And so if I take x to the 5th and divide it by x cubed, it's like I'm canceling 3 of the x's out from that x to the 5th, leaving me with 2 of them. So that's x squared. The other way that you might remember the rule is you're just subtracting the exponent. So I'm doing the 5 minus the 3 there. All right, continuing on. The 2 stays the 2 here. And then x to the 4th, I take 3 of them away, so I'm left with just 1. But of course, I don't need to write x to the 1. We just write it as the x there. And then minus the 35 stays the 35. And I'm taking out all of the x cubes here. And so that means that all of the x's are gone from that last term. All right. Now, like the last one, we look inside our parentheses and we look to see if we can go any further. And notice this one is a quadratic. That is, it does have the x squared in it. That's what tells me, okay, I can go one step further, at least potentially go one step further here. To do that, I'd have to add to the middle number and multiply to the last number. Is there a combination that does that? Yes, there is. And so we're going to get x cubed times 2 sets of parentheses with the x inside. The numbers that add to 2 and multiply to negative 35 are a positive 7 and a negative 5. And then that's our final answer, and that's what we're looking for. We're now switching back into solving our systems, which has been our theme for the last week and a half. So please solve this system of equations. Now, I'm kind of leading you in one direction, but do you have to make a graph for this? No. You do not need to make a graph for this. In fact, I would recommend that maybe you use a different method other than making the graph for it. So if we're not graphing it then, how can we then solve it? Which method do we call it when we set them equal to each other?
It's the substitution method.
Yep, substitution. Because you'll notice that both of these are set equal to y. If they both equal y, that means I can then set them also equal to each other, because I'm saying that y equals this, and therefore I can plug that in for y in the other equation. And if I do that, I end up with x equals 12, which is one small reason why you might not want to have tried doing this by graphing, because you'd have to make your grid go out to 12 there. And so to find my y value, I take what x equals, the 12, and I plug it back in for x into either one of the equations. Remember, you can choose whichever one you feel like plugging it into. And when we do that, we end up solving it and getting 101. This is definitely why graphing might not have worked out particularly well here. And so I want to talk briefly here, and this is going to be one of the things we talk about as we go, is how do we know whether we should or shouldn't use graphing to solve a particular system? In this case, this was actually one that was probably about the hardest that would be to tell. But usually, in order to tell if you can solve something by graphing, you'd really have to start going through the process of trying to solve it by graphing. Now, oftentimes, what you'll see happen is you'll end up with some really weird numbers. Either when you go and try to plot them, you'll end up with some funky decimals, or you'll end up with stuff that's way off the graphing grid. Or the reason why this one was a little bit tougher is because it ends up being revealed once we get to our solution. If you actually tried making the graph, you would end up seeing these two lines, which look like they are definitely getting closer together, but very, very gradually getting closer together. And it doesn't fit on a typical graphing grid to be able to see where that's happening. And so that's what would also be a clue for us. But we're going to see some other examples where it's even clearer just from the start whether we should or should not use graphing on them. And that'll be one of the themes we talk about today, is which method of the three that we now know to use. So we're going to go on to another one. We're going to be doing a total of 4 systems that we're going to solve together today. So please go ahead and write down this system and solve it. Now, the first thing you have to do with this is you need to be able to look at it and decide which method you need to use to solve it, because we have three options. And of these three options, we need to be able to nail down which one this would apply to. Now, the first thing I want to know is if we should be able to solve it by graphing. And this also affords us an opportunity to remind ourselves how we graph from standard form. So, to graph from standard form, remember that this is how we do it, where we plug 0 in for x, and then we solve for y, and then we plug 0 in for y and solve for x. And so basically, if I were going to be graphing this thing from standard form, the first equation, for instance, I would have to be doing 6 divided by 4. And I'd have to be doing 6 divided by 8. Are those going to give me nice, pretty numbers when I do them? No. And so what that means is that I don't really want to deal with graphing as a method here. It's likely to lead me into some funky stuff there. So stick with either of the two algebraic methods. Now for this one, is it going to be substitution or elimination? Yep, this one's elimination. And so we're going to be using elimination here, not substitution, because substitution means we have to have either a y equals or an x equals somewhere in there, and we don't have that. Elimination is typically when both of them are in standard form, and that's what you're looking at here. Now, elimination, that's where we add them. If I'm going to be adding them, then I need to be able to multiply them so that they add to 0, and one of them gets eliminated. You got two options, right? If I want the x's to eliminate, what would I multiply one of the equations by?
You multiply the bottom equation by 2.
Yeah, you could multiply the bottom equation by 2 to get there. And personally, that's the one I like the most, but it's not the only way to go. What if you wanted the y's to eliminate? Which equation would you multiply by what?
The bottom one.
Yeah.
The top one.
Yes, we could multiply the bottom equation by -8. Now, it would have to be a -8 because my signs are currently the same, and I would need my resulting signs to be different. Now, I did say that I like the x's, so I multiplied the bottom equation by 2. Notice the whole reason for doing that. The whole reason for multiplying the bottom equation by 2 is that now, when I take a look at my setup here, my x's are set up to where I have a -4 and a +4. Those are going to add to 0 and therefore eliminate when I add them. That's the whole goal of multiplying it. It's making it so that one of these will add to 0. And so I add them down and I get y equals -1. And so then to find my x value, I'm going to have to take the y that I just found and I'm going to have to plug it in. Now, typically, I do like to plug it into one of the original equations, but if you wanted to plug it into even the one you multiplied, that's fine. It's just that if maybe you couldn't read your own handwriting there, or you made a mistake getting there, or anything like that happened, that's going to become a problem. So I like to plug it into the originals just because there's less chance of a mistake happening. So I went ahead and just arbitrarily chose to plug it into the first equation. And so I plugged the y equals -1 in for y in the first equation, solve from there, and, well, I never said it would be an integer, did I? In fact, what we see here is one where not only would it have been tricky to actually try to plot the points of the original graph, but if you did that and made the graph, you'd be trying to figure out, okay, does it actually hit at 3.5? It wouldn't be clear cut about where our lines were intersecting if we made the graph. Now, they are actually intersecting at that point. It's just we wouldn't be able to have much confidence in that. And so these algebraic methods are really nice because they do allow us to figure out stuff that we wouldn't have been able to do just visually speaking there. And again, I want to start by talking about, for this one, which method we should be using, because that's one of the questions you're going to be asked a lot explicitly here at the start too, is just which method should we use for it. And so for this one, the first thing I'm always checking is, could it be done reasonably by graphing? And so let's start with the second equation this time, because it's just x equals. Can we graph x equals 2 minus 4y? Well, it's theoretically possible, but do you know how to do it fast and easy? No, that's not something we've talked about. So the odds are that's not something you're going to feel comfortable graphing. So that alone would eliminate graphing. You might also have answered that question by saying, well, I'd have to do 5 divided by 5 to graph the first one. That would work out. But then I have to do 5 divided by 8. That wouldn't work out real nice. And so that also would tell you graphing is not your best choice here. So between the other two, substitution and elimination, which one should we use? Yep, substitution. Not elimination. Because elimination means that everything has to be lined up. You know, x's above x's, y's above y's, equal signs above equal signs, and so on. And we don't have that here. Substitution means we have either x equals or y equals. And so because we have that second equation being x equals, that's the one I'm going to use. So I take what x equals and I plug it in for x in that first equation. When I plug it in for x in that first equation, remember, I am rewriting that first equation exactly as it was originally, except that instead of writing x, I'm writing the 2 minus 4y. When I do that, this is what I get. We end up with y equals 1.25, or 1 1/4 if you like the fractions. That's perfectly fine. I chose decimals mostly because they're just easier to type. This thing doesn't type the fractions real well. And so now that I have my y value, I need to find my x. Well, remember, to find the x, I can plug it back into either equation, but in this case, one of them definitely seems easier than the other one. Plug it into the second equation, because you notice I'm trying to figure out what x equals, and the second equation tells me what x equals. It's set up to figure that out. And so I'm going to plug it into the second. Could you plug it into the first one? Yes, absolutely. But the second one seemed easier. So I plug it in there, and I get that x is -3. And so then we have our final solution of -3, 1.25. And we're done. For this last one we do together, yes, I am going to challenge you with slightly bigger numbers. But just because the numbers in order to get there are a little bit bigger, it doesn't mean the answers are necessarily bigger. You actually have to work it through to find out that part. I will give you a hint though, they're not integers on this one. And again, the first thing you do is you think about which method to use. Graphing is definitely not a winner here because like they're in standard form. In order to graph from standard form, I'd be plugging 0 in for x and solving for y. That gave me 1.7. That's not an easy number to be able to plot, let alone trying to do 17 divided by 12 to find the y value. And so that's why we do not do graphing. And then between the other two, since they're both in standard form, you're going to be using elimination. And when doing elimination in this one, you really have to make some choices because you can have either the x's eliminate or the y's eliminate. I think they're both about as easy. And just pick one and then decide, okay, what can I multiply each equation by in order to make them the same? Now, if you're feeling totally stuck on how to do that, I was looking at it, and when I did it, I said, okay, I can make these first two, I can make my x's both into 36s. That's what jumped out to me. And so if you're needing a little bit of a nudge here at the start, this is what I multiplied by in order to be able to get us there. And so when I multiply by those, this is what I end up getting. So just so you can kind of see at least one way that the work could look. Again, yours might look different. It all depends on what you chose to multiply by. And then once we know our y value, I'm going to plug it back into one of the equations in order to figure out what the x value is. And again, I have choices here. In this case, I have 4 definite choices about what I plug into. Well, those second two, the numbers are really big, so I don't really feel like plugging into one of those. So between the first two, which one do I want to plug into? It doesn't really matter, but you know, I can multiply something by 10 pretty easily in my head. I wouldn't need a calculator with that. So I went ahead and plugged it into the first equation. And when I did that, I ended up getting x equals 4.3 repeating, or 4 1/3. The one thing I do not want you to say for that answer is 4.3. All we have to do to make it exact is put that little line above it to show that the 3 is repeating. Whereas if you leave that out, it's just 4.3. You rounded it quite a bit and changed the value quite a bit. So when it's especially that easy to write it exactly, do so. The last thing I'll mention and try to bring back is notice what our algebraic methods are doing for us. Our substitution and elimination methods let us find the solution. If you've been doing this by graphing and you saw your two lines crossing at that point, you'd be saying, okay, what did I do wrong? You would be swearing that something had gone off along the way. So that's partly why we need to have these algebraic methods so that we can figure out some of these wonky points that do naturally come up.